Hi, nice to see you all watching our presentation, and I would like to tell you something about our project, about neuron recycling that we've been doing with Kuba Krajewski, and I'm Maciej Pióra. The project leader is Sebastian Jaszczur, our scientific advisor, so the person who oversees the project is Marek Cygan, also present, and we're working on we've been working on this idea at IDS and NCBR, and that's is our master's thesis. Okay, let me just. Okay. Okay, so the outline of the presentation is is here. So first we're gonna introduce the most important concepts and tell you about the most promising approaches we've been trying, some interesting ideas we've stumbled upon during our journey, and how the project ended and what are the conclusions. To just tell you something about the whole premise, some of you might be familiar with the idea of pruning. Pruning is getting rid of parts of neural networks, so getting rid of weights or neurons in a neural network by just setting the value of the weights or the value of activations of neurons to 0. Another important thing is the lottery ticket hypothesis, and the lottery ticket hypothesis says we've got big neural networks, and some of the neurons in the networks are doing a lot of work, most of the work. Other neurons are pretty much useless, and we can prune them. Why is that? Well, the idea in LTH is the neurons that are doing all the work, those neurons got initialized properly. They were just lucky. So let's combine the idea of pruning and the idea of lottery ticket hypothesis. Let's reinitialize some neurons in a neural network. So if we see a neuron isn't doing anything and, well, it got dealt a bad hand at the initialization time, well, let's just draw another ticket. Maybe it's gonna work this time.
Yeah, so now I will shortly describe the architecture. In a sense, I will describe which parts of the model we tried to attack, which parts of the model we wanted to modify, and see what's happening. So this is the whole transformer architecture that you are probably familiar with. There are two main parts that constituted attention and feed-forward networks, and a lot of effort has been put in modifying or working on attention. However, most of the computation is done in the feed-forward layers that turn out to be very important for the final outcome of the network, and are in some sense so simple that not too many works are done to understand and modify them, and we wanted to explore these parts in a little more. Yeah. So basically, as we mentioned, we wanted to recycle neurons. So by neurons, we mean single units on this graph, which in terms of like mathematical implementation are row and corresponding column in first and second matrix in the feed-forward layer of transformer, because this feed-forward layer is basically two linear layers with some non-linearity between them. So yeah, these are the two matrices that we will be dealing with in the next parts. And for the specific type of the model, we have decided to use the BERT architecture, because basically it's simple. We already had some existing code base, and this is like a model that is very important in many practical scenarios in business. So kind of improving efficiency, making this model work with lower amounts of compute would be a very beneficial goal to achieve. So now we will describe main approaches that we have taken during our project. So the basic idea from the beginning of our project was recycling. So there are two main stages. First, we need to identify the neurons to get rid of. And then the second stage is we want to put new weights on these neurons. So for the first part, we have decided to use magnitudes or norms, which is inspired by pruning. This is a very simple heuristic for choosing less important parts of network, but it turns out to work very well. We also tried learnable approaches for choosing the least important neurons, but finally the simple magnitude heuristic turned out to work best. And by magnitude we mean here that we calculate a norm of the row from the first matrix, and we also calculate norm of the corresponding column in the second matrix, and we multiply these two numbers. For the second part, we have explored various initialization distributions. Our first attempt was to basically reinitialize according to the distribution that is used in the initialization of the layer. But it turns out to have problems in a sense that often the magnitudes grow gradually during training. So when we reinitialize to the initial weights, we will have even lower magnitudes on the weakest neurons, and we will reinitialize over and over the same parts of the network, which is of course not what we want. So we modified that to match the current distribution of weights in the layer. And another approach that also is described in literature in terms of growing neural networks, so adding new neurons to the networks, was copying existing ones.
When we tried recycling neurons, one of the first issues we encountered was that sometimes a neuron got recycled in one recycling step, and then after, let's say, 1,000 or 10,000 steps of learning, we had another step of recycling, and exactly the same neurons got recycled. And one of the ideas we introduced to try and tackle that problem was immunity. So that was just, giving a index to each of the neurons, saying for, let's say, 10,000 steps, this neuron cannot be recycled. And it didn't really work well because we got rid of all the neurons that weren't doing anything, and at some point there were no neurons that didn't do anything left, and we had to recycle the ones that were working, so that approach didn't end up well.
Another problem that we have identified and is illustrated in these spikes in the loss. This is of course zoomed in very much. But we identified a problem that the operation that we are doing is discrete. So at some point we are choosing a fraction of the network, and in one moment changing the weights of this part. And it was hard for in the first moment for the optimizer to adapt to that. So we have decided to try to mitigate this issue, but by making this technique more smooth. And the strategy to do this was that we were choosing neurons to recycle at each recycling step. We were also choosing the target weights for each of these neurons, but we were moving to the new parameter values gradually in some steps by linear interpolating, while freezing the old value and making the new value learnable. So this was a kind of approach to that, which helped us in making this whole process smoother. However, we still had the problem that small recycling fractions were not changing the final outcome of the network very much, and with high recycle ratios we were hurting the network too much to make the performance better. So during our project we have also taken some additional research directions. We have explored other interesting topics, and now I will shortly describe these topics. First topic that we wanted to get more experienced with was exploring neuron magnitudes. We were trying to recycle neurons based on this metric, so we wanted to see how this metric behaves throughout the training. As our method can be interpreted as modifying the distribution of neuron magnitudes throughout training, we wanted to see what is the current distribution, how it evolves during the training process, and also we wanted to find out what is the ideal distribution of these magnitudes. And for this part, we tried overtraining of the network, which was freezing some parts of the transformer and only training whole feed-forward layer, or only training neurons with lowest magnitudes, random neurons, or with highest magnitudes. And we wanted to see which option gives the best performance and what are the differences in the neuron magnitude distributions. And you can see that in the baseline scenario, without any additional feed-forward training, the distribution of magnitudes is skewed to the left, so there is a relatively big number of neurons with very small magnitudes. Additional training of the whole feed-forward networks, already makes the distribution more even, while training the neurons with lowest magnitudes, which was giving the best performance, makes the distribution the most even.
So when we started thinking about modifying the distribution of the weight of the magnitudes of neurons, one of the things we thought about that could well somehow impact that would be weight decay. So from the beginning of the project we didn't use weight decay at all because we wanted to minimize the number of variable factors. Once you start introducing weight decay, then you can ask yourself, should I introduce dropout? Should I use some other weird technique? So we didn't do that, but at that point we wanted to see what weight decay does to the neurons, and that's how what's the distribution of the magnitudes in T5 in BERT in a available checkpoint, and it's pretty even. It looks really nice. And when we take a look at the distribution in T5. We can see that it's a bit scary compared to what we could see before, and the reason for that is this one wasn't trained with weight decay and the previous one was using weight decay. So that's what weight decay does, and that might be some idea why weight decay works. And so what we tried to do was come up with an idea to do something similar. So, you know, let's get the weak neurons, let's push them forward, let's get the big ones, let's put them, let's slow them down a bit, and let's see if that influence on the distribution does something good. And yeah, so that's the idea, right? If something's really small, let's push it a lot. If something's just right in the middle, let's push it just a bit. We also have to remember about the big neurons. If we push all the neurons in the direction of the mean value, the training is gonna explode. So we have to work with all the neurons. But unfortunately, it also did not work. Well, it wasn't. Well, I think it wasn't better than weight decay. We might have, like, if we tweak the parameters a lot, we might have gotten it to work as good as weight decay, but not better. If we could see on the graphs that we are modifying the distribution, so that's the brown line, I think. And the distribution, let's say that's on the right graph, then the performance of the loss was worse. And okay, so that's it about what we've done.
Yeah, so now we would like to finish this presentation with takeaways that we think are like the most important. So as you've seen, we've tried several ideas that didn't work as we planned in the beginning. However, we have gained many interesting insights about training dynamics of language models during performing all of these experiments. Still, many researchers point out that efficiency or sparsity are very promising research directions in machine learning, also in language models. And we believe in that. So now we are planning to use our experience in a follow-up project involving mixture of experts. So that's it for our presentation. Thank you very much for your attention.